Hello everyone, my name is Marcos. I'm a PhD student at ICMC-USP. My advisor is Regilene Oliveira and my co-advisors are Alex Rezende and Juan Carlos Artes. Today I'm going to talk with you about the study of a bifurcation diagram of a family of quadratic differential systems. And I will explain you how we classify the phase portraits that we obtained in this study. Here we call quadratic differential systems of this form, where P and Q are coprime polynomials in this ring, and the maximum of the degree of P and Q is 2. We already know that the complete characterization of the phase portraits for real planar quadratic vector fields is not known, and attempting to topologically classify these systems, which occur rather often in applications, is a quite complex task. In this book here, these authors classify the structurally stable quadratic vector fields, also known as a codimension 0 vector fields. This classification was done modulo limit cycle. After that, 20 years later, in this book here, these authors classify the structurally unstable quadratic vector fields of codimension 1. This classification also done modulo limit cycles. The next step is to study the structurally unstable quadratic systems of codimension 2 as the combination of elements of codimension 1 modulo limit cycles. The approach is the same as used in the previous two works. One must start by looking for all the topologically possible phase portraits of codimension 2 and then try to realize all of them or show that some of them are impossible. So, it is also very convenient to have studied the bifurcation diagram that contains all the required phase portraits in order to prove the realization of them. So the main goal of this talk is to present the study of the bifurcation diagram of the class, this one, of all real quadratic polynomial differential systems which have a finite saddle node, a simple finite singularity, and also an infinite saddle node formed by the coalescence of a finite and an infinite singularities. From this paper here, we get the normal form that describes family which we are studying. This is the normal form that we want. This normal form depends on 4 real parameters, and this condition must be fulfilled. So, we saw that the normal form 1 depends on the parameters C, E, H, and M and R4. With a simple rescaling on time, we conclude that we may rewrite systems 1 depending on these parameters here. So instead of considering as a parameter space the set R4, we may consider the real projective space RP3. Additionally, with a simple rescaling in the variables, we may assume that the parameter H is 0, or if it is non-zero, we can take it equal to 1. So in fact, we can see our bifurcation diagram as a ball, and inside the ball we are in the affine part of the bifurcation diagram. We consider h equal to 1, and in the border we consider h equal to 0. We foliate the three-dimensional bifurcation diagram by planes m equal m0 with m0 constants plus the open half sphere h equal to 0. In those planes m is equal to m0, the coordinates are c and e, and in fact, for each plane here, we are indeed in correspondence with an ellipsoid in the ball. Okay? So the main technique used in the construction of the bifurcation diagram is the invariant theory for quadratic systems, developed in Sibirski School in Moldova, especially improved by Professor Nikolai Volpe. I will not explain this theory here, but I recommend you chapter 4 from the PhD thesis of Professor Alex Carlos Rezende for a very nice summary on this theory. We already know that in order to classify all the global phase portraits obtained by the study of some family, one must start by verifying all the topological chains, the bifurcations, in the behavior of the solutions of this family, depending of course on the real parameters of this family. In what follows, I present you the algebraic and non-algebraic bifurcation surface that we consider in our study. Here we have S2 in green. Along this surface, we have the following phenomena, when the finite saddle node becomes a cusp-type singularity. This happens along this plane here. S3 in yellow, when we have finite weak singularities, which occurs when the trace of a finite singular point is 0. This equation is given by this plane here. S4 in purple. This surface will contain the points of the parameter space where we have necessary conditions for the existence of invariant straight lines. This surface is split in some regions. Depending on this region, the straight line may contain connections of separators from different points or not. So, in some cases, it may imply a topological bifurcation, and in others, just a infinite bifurcation. The equation of this surface is given by this equation here. And in fact, for h equal to 1, we have these four planes here in this picture. S5 in red. This surface indicates when we have a coalescence of infinite singularities, and its equation is given by this expression here. And for h equal to 1, we have this picture. S6 in black. When one finite antisaddle churns from a node into a strong focus, and its equation is this one. For h equal to 1, we have this double cone here. S7. Here we put all the non-algebraic bifurcations that we detect in our bifurcation diagram by using numerical tools. Okay? In S8, light blue, here we consider all the degenerate systems that we obtain in our bifurcation diagram. By a degenerate system, I mean a system possessing a curve filled up with singularities. Okay? Along this surface here, one may find weak singularities of order 2 or higher. After defining all these surfaces, we make a geometric study of the behavior of the algebraic surfaces concerning their singularities, intersection, and extremum points with respect to the parameter m. After this study, we conclude that the set of the needed algebraic singular slices in the bifurcation diagram of family QSN SN11 is formed by these elements here. Note that the indexes here are not consecutive, since we reserve some numbers for other slices not algebraically determined, and for, of course, the generic slices. But in total, we have 54 slices to be studied. So, we choose here an integer greater than 3, we choose 4, in order to be the most generic slice in our bifurcation diagram. We make a complete study of this slice here, m equal to 4. We obtain here one piece of non-algebraic bifurcation surface, here another one, and here two new ones. This yellow region is a region containing limit cycle. Okay? After we study completely this slice, we pass by the slice at infinity, m is equal infinity, as we obtain a complete coherence between surfaces and phase portraits from regions from m equal to 4 and regions here from m equal plus infinity. We conclude that no more slices greater than 4 are necessary to be studied in our bifurcation diagram. So, after that, we start moving down from slice to slice and explaining all the changes that occur. From the study of the remaining 52 slices, we found several interesting phenomena, including a coalescence of two non-algebraic surfaces, the presence of a non-algebraic bifurcation surface due to a bifurcation of a double limit cycle, and also examples of phase portraits possessing 3 limit cycles. In total, after we finish the study of the complete bifurcation diagram, we conclude that it has 631 parts, divided in this way. This partition is obtained by considering all the bifurcation algebraic and non-algebraic surface, modulo island. By modulo island, I mean that we hope that we did not lose anything in our study. Okay? So how do we classify the 631 phase portraits that we obtain? Well, we introduce some invariants, and we actually choose integer-valued invariants, character invariants, and also symbol invariants. We define an invariant called I, which is I1 until I14, where, for instance, I1 gives us where we have non-degenerate systems and degenerate systems, as I explained before. In this case here, the systems possess two straight lines filled up with singularities intercepting at the finite part. Here we have a parabola filled up with singularities, and here we have a hyperbola filled up with singularities. I2, for instance, gives us the sum of the indices of the isolated real finite singular points. I3 is the number of real infinite singular points, and so on. We go up to I14, and with these 14 invariants, we could distinguish among all the 631 phase portraits, and as a result, we conclude that there are 226 topologically distinct phase portraits for the quadratic vector fields in this closure. Here I'm presenting the 226 phase portraits. Okay, 7 pages. As a result, we conclude that the following corollary. There are 40 topologically distinct phase portraits of codimension 2 modular limit cycles in this closure. Additionally, they are examples for the realization of all the phase portraits from the set of quadratic systems possessing these two saddle nodes, as I explained before. This study is done in this preprint here. Okay, so that's it. Thank you very much for your attention. Thank you also the organizer for the opportunity. That's all.